Often in physics or math, we find ourselves needing to integrate a certain function over a surface or a volume. Some examples that appear in first year physics are rotational inertia, which is integrating over a volume, and the electric flux, which is an integral over a surface. Now, normally, you would need to use multivariable calculus methods to do these integrals. But this isn't always the case. Sometimes, if the function and the shape itself that we're integrating over can be parametrized in terms of one variable, and they have a nice symmetry to them, we can do these multivariable integrals using just one variable. And I'm going to showcase that technique in the next few videos. So let's start by attempting to find the area of a circle. Assuming the only thing we know is the value of pi, which is the ratio of the circumference of a circle to its diameter, let's do this. So first, we have to break up this circle into multiple areas that we want to sum over, because that's really just what an integral is. Now we can do this two ways. So here's the first method. This circle can simply just be rewritten as the sum of many small pizza slices. And these pizza slices go all the way around the circle. So in other words, we're going to break the circle up like this into many small slices. And we want to find the area of these slices and then add it all together. And the whole point of calculus is taking many sums and making them infinitesimally small so we can find the total area of this. So we're going to assume that all of these pizza slices are very, very small. All right. Now, the area is simply going to then be the integral of dA, which is going to simply be the area of one of these slices. But what is the area of a slice? If we look at it closely, a slice is almost a triangle. And as we take the limit, as it gets smaller and smaller, this curve starts to appear more and more straight. And then it simply becomes a triangle. Now, what are the dimensions of this triangle? Well, this side right here is going to be r, and this right here is going to be some arc length. We'll call it ds. In the limit, this slice will become a triangle, and its volume will be r times ds divided by 2. So we have, this is simply just the integral of r ds over 2. And now we want to see what ds ranges from so we can calculate this integral. So in the calculation of a circle, we'll be starting at 0 arc length, and we'll be rotating around the circle and summing up until we reach the end. So in other words, we want to go a full circumference around. So that means the bounds of our integral are going to be 0 to the circumference, which is just 2 pi r. So then what's this area? Well, the area is just the integral of this, which is r over 2 times s, evaluated at 2 pi r, and 0, and that's just pi r squared. And now let's move on to the second method. Let's now use the fact that this circle can be described using just one variable, its radius. So we want to find small areas that can be described by this radius. So that can be done just by drawing smaller circles inside this big circle. But this needs to be an area, so let's take these rings. Then the area of this circle is simply just the sum of these small rings. And of course we're assuming that the area of these rings is infinitesimally small. So that must mean, well, since this length is obviously can't be infinitesimally small, that must mean the width must be very small. So then what is this area? Well, the area is just the sum of all these small areas. And what is the area of each ring? Well, let's assume we have a ring with a radius of small r. And of course, this is going to be smaller than capital R. Well then, let's imagine breaking up this ring, splitting it right here, and elongating it. So this ring is simply equal to, or close to equal to, this strip. And what are the dimensions of the strip? Well, the length is equal to the length around this ring, which is simply the circumference. So that's going to be 2 pi r. And the width is going to be some small change in r. So here we have r1, r2, a small difference between this. That's just dr. So the area is going to be 2 pi r times dr. And what are the bounds of integration? Well, since we're integrating across r, from what values does r vary from? Well, since we're starting at a very small ring, r will start at 0, and then we'll go all the way up until we reach the end of the circle, which is a radius r. So we'll be integrating from 0 to big R. And if we just do this real quick, we have 2 pi r, r squared, evaluated from r to 0, r squared over 2, and that's just going to be pi r squared.